السلام عليكم. إن شاء الله هذا بيكون الجزء الثاني من هيكل عاشر متقدم. Coulomb's law tells me that there is a force between any two charges, whether it's attraction or repulsion, and we calculate it using Coulomb's law. So the equation is F is equal to K, the first charge, the second charge, divided by the distance between the first and the second charge squared. So here we will see what is the relation between F and the first charge. When the first charge value increase, the force increase. When the value decrease, the force also decrease. Same thing with the second charge, Q2. If the value of Q2 increase, the value of force increase. If it decrease, the force also decrease. Now if we go to the distance is inversely proportional. So here we say that force is proportional to Q, force is proportional to Q, the second one. And when we deal with the force and the distance between the charges, here we say that they are inversely proportional. So when R increase, the force decrease, and when R decrease, the force increase. But they don't increase or decrease linearly because there is a square on the R in this case. We call this inverse squared law. So this is the proportionality with the charges. So now to make the equation, we need to remove this and add a constant. This constant will be the value of K. So the definition is Coulomb's law says the magnitude of the force between point charge A and point charge B that are separated by distance R is proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. Now the unit of a charge is Coulomb. This is for charge. And the value of the constant K is 9 times 10 to power 9. So this is the value of K. So here we have force is measured in Newton, Q is in Coulomb, Q is in Coulomb, and distance must be in meters. Now these forces are the same on one charge and the other. So here we have positive and positive. So if the charge A is repelling charge B will go to the right because A is forcing it to go to the right. The same thing happens with the force on charge A. So B is forcing A to go to the left. So both of them affect each other with the same amount of force in opposite directions. So we have FB on A, F because B is forcing on A, and F A on B because A is forcing on B. Now the same thing you have when you attract two charges. So A will go to the right because B is attracting it, and B will go to the left because A is attracting it. Another note we need to know is the magnitude of the charge of a single electron or proton, depends on the question, is known as the elementary charge, and it has the value of 1.6 times 10 to power minus 19 Coulomb. Of course, force is a vector quantity, so you need to draw the direction of the force. It depends on is it attraction or repulsion and in which direction. So here we say the electrostatic force is a vector quantity. So I will leave this for you to read. Let's go to the questions. Charge and distance. What is Coulomb's law and how does it allow you to describe and predict the effects of electrostatic force between distant objects? So as we said, it's a force that is proportional to the product of the two charges and inversely proportional to the distance between them. So how do we write it? We say F is equal to K Q1 or QA times Q2 or QB divided by the distance between the first charge and the second charge. Moving on to the second question, force and charge. How are electrostatic force and charge related? Describe the force when the charges are like and when the charges are unlike. So like we said, force is proportional to the value of Q or the charge, and when you have two charges, if they are same as in positive and positive or negative and negative, it will be a repulsion force. And when you have opposite type of charge, positive and negative or negative and positive, they will be attracting. Next question. Force and distance. How are electrostatic force and distance related? And how would the force change if the distance between two charges were tripled? So we said that force is inversely proportional to the distance squared, and when you have a distance that has been tripled, it means that instead of r, now you have 3r. So the 3r, you will put them in the square, so you get 3r squared. Now how much do you get? You get 9r squared, and this is in the denominator, so you have 9r squared. This means that the force will decrease by 9 times. We said that if r increase, the distance increase, it means the force will decrease, and if it decrease, the force will increase. Here are the answers. Moving on. Electrostatic force. You have two charged spheres are held at a distance r apart as shown in the figure. Compare the force of sphere A on sphere B with the force of sphere B on sphere A. Like we said, this will be repelled to the left by which force? Force B, that is affecting A, and this will be also repelled to the right by force of A on B. But if we compare the magnitude, we will say FBA will be equal in magnitude but opposite in direction of AB force. Next question, critical thinking. Suppose you are testing Coulomb's law using a small positively charged plastic sphere and a large positively charged metal sphere. According to Coulomb's law, the force depends on 1 over r squared, where r is the distance between the centers of the spheres. As you bring the spheres together, the force is smaller than expected from Coulomb's law. Explain why is this happening. So basically, let's draw. Here you have the first sphere, and here you have the second sphere. Let's say this is the metal, and this is the plastic. So here on the metal, we have positive charge everywhere. And here we also have positive charge on this side, because an insulator will have the charge only on one side. So when you bring them closer to each other, okay, what happens is, it says here that the force is getting smaller although you are bringing them closer to each other. Now what happens is there is a repulsion force between the positive on either side, and you will have all the positive coming far away on the metal side, and here you will have the positive where it is. So the charge will go away from this side because this positive is repelling this positive. So you are actually increasing the distance between the charges. That's why the force becomes smaller than the objects being closer to each other. Here are the answers. Let's go to the next question. Here you have charges on spheres. Two spheres of equal masses m and equal positive charge q are a distance r apart, as shown in the figure. Derive an expression for the quantity of charge q that must be on each sphere so that the spheres are in equilibrium. That is, so that the attractive and repulsive forces between them are balanced. So what we are talking about here is the force of attraction, which is G mass 1 mass 2 divided by the distance between 1 and 2 squared, and the electric force, which is K Q1 Q2 over R 1 2 squared. So here we will say that the force of gravitational attraction is equal to the force of electrostatic. Here we are talking about in magnitude. So let's substitute G m1 m2 divided by R 1 2 squared is equal to K Q1 Q2 divided by R 1 2 squared. Now we have the same mass, so we can say mass squared, and here we can say G over R 1 2 squared. and here we have the same charge, so we can say it is Q squared over R12 squared. Now we can cancel the distance because it's the same separation between them, and we need to find what is the value of Q. So here we will say that Gm squared is equal to KQ squared. Now to get rid of the K and the square, we need to divide by K and take the square root. So we divide both sides by K first. This K will go with this K. You get Gm squared over K, and this will be Q squared. Now we take the square root of both sides, and this will be cancelled with this, and the square on the M will also be gone. So here we will get Q is equal to M and multiplied by square root of G over K. So that's the first part. Let's go to part 2. How would doubling the distance between the spheres affect the expression for the value of Q that you have determined in the previous problem, which is part 1? Basically here there is no distance in the equation, so we will say Q does not depend on R because there is no R in the equation. Let's go to 3. Assuming that the mass of each sphere is 1.50 kilogram, determine the charge on each sphere needed to maintain this equilibrium. So in part 3 we will only substitute. So we have Q is equal to, how much is the mass? He said 1.50 kilogram. And then what is the value of G? G is a constant, 6.6 times 10 to power minus 11, and Coulomb is a constant, 9 times 10 to power 9, and the answer will be 1.28 times 10 to power minus 10 Coulomb. So these are the answers for you to check. Here are some questions on Coulomb's law. A negative charge of minus 2 times 10 to power minus 4. So we can name it, this is Q1. The first one comes in the question, give it number 1. The second one, give it number 2. And there is a positive charge, this is the value of Q2, are separated by 0.3 meters. So this is R. What is the force between them? So you need to calculate the force. So we say F is equal to K, the first charge, second charge, over the distance between 1 and 2 squared. Substitute, we have 9 times 10 to power 9. And then charge 1, we don't use the signs, so you will only say 2 times 10 to power minus 4 and 8 times 10 to power minus 4. Divided by the distance squared, so you have 0.3 squared, and the answer will be 1.6 times 10 to power 4 Newton. And this is the force of attraction because you have a positive and a negative charge. Going to the next question, question 10. This is question 9. A negative charge of this much, so we call this Q1, exerts an attractive force of 65 Newton on a second charge that is 0.05 meter away. So this is the force here and this is the distance R. What is the magnitude of the second charge? First of all, the second charge should be a positive charge because it says this is an attractive force and the other one is a negative charge. So here we say F is equal to K, first charge, second charge, divided by the distance between them squared. Now, do I have the force? It is 65 equals to, do I have K? It's 9 times 10 to power 9. Do I have the first charge? It is 6 times 10 to power minus 6. And this Q is unknown, divided by the distance, which is 0.050 squared. We do shift solve, and the value of Q will be equal to 3 times 10 to power minus 6 coulombs. Let's see this question. Here you have sphere A with a charge of this much. So this is Q of A is located near another charge B, where the charge B, this is QB, is equal to this much, and this is the distance R between A and between B to the right of A. So here is A and B charges. You have A to the left and B to the right, and the distance between them is equal to 4 centimeters. So you need to know how to convert centimeters. Now part A says what is the force of B on charge A. So you go to charge A and see, does it go to the right, does it get attracted, or does it get repulsed? So in this case it will be attracted because it is positive and negative charge. So in this case you have attraction. Now in part A we will calculate force of B that is affecting A, and this will be equal to K QA QB divided by the distance AB squared. Now we substitute with the numbers. We have 9 times 10 to power 9 times the first Q is 6 times 10 to power minus 6. Of course you need to know what are the converters. So when you have C you divide by 100. When you have mu you multiply by 10 to power minus 6. When you have M you multiply by 10 to power minus 3. When you have N you multiply by 10 to power minus 9. So here we have minus 6, and the second charge is 3 times 10 to power minus 6 over the distance between them, which is 0.04 squared. The force we get will be 101 Newton. In which direction? It will be to the right direction because it will go to the right. Let's go to part B. A third sphere C now is added. This is the Q of C. If it is located 3 centimeters beneath means it is under charge A. So this is the distance between A and C. What is the new net force on sphere A? So here we have to draw the forces on the diagram to know where is charge A going to go. Now in part B we already found that BA is equal to 101 Newton in the right direction. Now we need to find the force of C that is also affecting A. So here we will substitute directly. You have 9 times 10 to power 9 times the charge of A is 6 times 10 to power minus 6. The charge of C is 1.5 times 10 to power minus 6. And the distance between them is 0.03. This is equal to 90 Newton. In which direction? Let's see. So here you are being repulsed by C, so A is gonna go up. So this is the force of C that is affecting A, and this is the force of B that is affecting A. So in this case this will be up. Now we have two forces that are perpendicular to each other. How do I find the total net force in this case? So here we have the first force, which is FB on A to the right, and we have force of CA up. So where is charge A going to move? Somewhere in this direction. So this is the force on charge A. Now how do we calculate it? Of course we need to do Pythagoras. So force on A will be equal to the square root of FBA squared plus FCA squared. And now we substitute with the values. We have 101 squared plus 90 squared, and this is equal to approximately 130 Newton. Now where is the direction? You need to find the angle theta. So let's find it. Theta will be tan inverse of the force on Y divided by the force on X. So we say FCA over FBA. If you have a sign, you put the sign with it. So we say tan inverse. FCA is how much? 90 over FBA 101. So the angle will be approximately 42 degrees. So this will be 42 degrees. Now here it says, based on the previous problem, you replace the charge B in the example problem with a charge that is positive 3 microcoulomb. What is the new situation, and find the new force on charge A. I will leave this for you to solve, and at the end the answer will be same amount of force, okay, but the theta will be 138. Now what changes is, here is sphere A, here is sphere C and here is sphere B. Before we had an attraction between A and B. Now both of them are positive, so in this case there will be a repulsion, so the force will be the other way. This will be force B on A. Now, and then we have the same repulsion between C and A, so the force will also be up in this case. This is force CA, and the charge will move again in this direction, but then my angle will be from the 0 all the way to here, so it will be 138 degrees. Let's see this question. Describe how electrostatic force between two charges change when the distance between them increased to 3 times. Tripled, it means you multiplied by 3. So instead of r, now we have 3r. Now 3r will be 3r squared. Now 3r squared is 9r squared, and then you put it in the equation. F is equal to 1 over 9r squared. It means that F decreased by 9 times. This is the answer. Next question. This is also like the example. You have 3 charges. I will draw it for you and then I will leave the answer for you to solve by yourself. Sphere A is located at the origin. So here we have 0. This is sphere or charge A and has a charge of plus 2 times 10 to the power minus 6 Coulomb. Sphere B is located at a distance to the right. So we assume that this is at the origin, x is equal to 0, and then you have a distance of here 0.60 meter. This will be the charge B, and the value is a negative value. And also you have another sphere QC at a distance of 0.80 to the right, and the value is positive. And we need to know what is the net force on charge A. So let's draw the forces. It will be attracted because of B on A, but it will be repulsed because of force C on A. So in this question, what do? We find FBA to be how much, and then FCA to be how much, and we notice that they are opposite in direction. So what do we do in this case? We will say that the force on charge A, I always prefer to do it this way, right minus left, as in the force on the right minus the force on the left. So the right one is FBA, the left one is FCA. Now if you get a positive answer, it means it will go right, it will move to the right. If you get a negative answer, it will move to the left. Same thing is for question 14. Determine the same procedure but for the force on B. So in this case, you will calculate FA on B and FC on B. Electric fields near conductors. Here, if you have a conducting sphere or a hollow sphere, what do you have? You have the whole charge of the body distributed over the whole surface, of course evenly, so they will be repelling each other and distributed over the whole object. Now if you have a hollow sphere, it's empty on the inside, so the charge cannot go inside, it will be only on the surface, only the outer surface. What about if you have an irregular surface? So in this case, you will have more charge here because you have a sharp edge, okay, and you have less on the surface that is flat. An example of these are the lightning rods, because they are attracting the lightning. They are put on buildings to protect them from lightning. They are called lightning rods, and the charge in a cloud sparks the rod and then it goes to the ground by grounding the lightning rod. So here we have a question, but first we will go over the content from the lesson. This question is on capacitance, and capacitance is like a property of a capacitor to store energy. So here we have capacitance is calculated using farad unit, and 1 farad is equal to 1 coulomb over volt, and we have charge is in coulomb and the potential is in volt. So here is question 61. A sphere is charged by 12 volt, so this is delta V, and suspended above Earth as shown in the figure. What is the net charge Q on the sphere if you have C, which is the capacitance, and this is your delta V? So we say C is equal to Q over delta V. Do I have C? Yes, it is 5.3 times 10 to power minus 11, and Q is unknown and delta V is 12. So we do shift solve and you get Q equals to 6.4 times 10 to power minus 10 Coulomb. Now we go to Millikan's oil drop experiment. Here you have an atomizer, which is a small bottle that have oil in it, and then you have oil sprayed. Now here you have two plates. This is a battery and this is the positive side, which is connected to this plate, so this one becomes positive plate, and this is the negative side of the battery, which is connected to the negative plate. Now when you have positive and negative plates, what do you have inside? You have a uniform electric field, so it will look like this, an electric field inside that looks like this. Now when the oil drop goes here inside, it is charged, it will go down. So these oil drops are charged by friction when they first enter into the chamber. So they have mass, so they have Fg, and they will start going down because of Fg. Now depending on the size of the oil drop, it will be closer to or far away. Now he was trying to suspend a negatively charged drop. So how do you suspend it? Here, this is your positive plate, this is your negative plate. If you have a negative charge, where does it go? It will go against the line of the electric field. So this is the electric field line, and the charge will go up because of the electric force. But it has a mass, so because it has a mass, it will have Fg down. Now when they are equal in magnitude, opposite in direction, what happens is the electron or the negative charge oil drop will be floating in the air. So here we say that charge or oil drop is suspended. Why? Because Fe is equal to Fg in magnitude and opposite to it in direction. So the downward force from Earth's gravitational field and the upward force from the electric field are equal in magnitude, but they are opposite in direction. Then he calculated the magnitude of the electric field from this equation and found the weight of the drop by mg. This is Fg force, and then he turned off the electric field or the battery and measured the rate of the fall of the drop. Yani after it is suspended here, it fell down because there is no electric field. Now after you turn off the electric field, now we have electric field is off and we have our negative charge here. There is no electric field, so it will start going down. It will go down because of Fg, but now there is no electric force, there is drag force. Drag force is from air resistance because there is air in the chamber here. So what happens is the electron will reach something called terminal velocity. When do we reach terminal velocity? Is when you have Fg is equal to Fd. So the object will not fall freely down. No, it will be moving at a constant velocity, which is known as the terminal velocity. So this one will be a constant velocity. Then he was able to calculate the value of the charge on the drop from the weight, which is mg, and the electric field E. He found that the net charge on the oil drop is always some integer multiple of 1.6 times 10 to power minus 19, which is, like we said, charge or elementary charge cannot be 1/2, half, 3/4, and so on. Let's see this question. A drop is falling in Millikan's oil drop apparatus with no electric field. So if there is no electric field, then what are the forces that are acting on the oil drop regardless of its acceleration? If the drop is falling at a constant velocity, describe the forces acting on it. So the first we will discuss when you have electric field. The second, when there is no electric field. When you have electric field, this is your negative charge. You will have Fg down and you will have Fe up. How do you find this? From the equation Q times E. How do you find this? From the equation Mg. Now when there is no electric field, it means now it is freely falling. So you have Fg down, but you have F drag above. F drag has a different equation depending on the situation that you have. Fg is calculated by Mg. Now here we have no electric field. It means this is the case that we are talking about. So what are the forces? You have Fd and Fg. Fg is down and Fd is up. Now in part 2 it says if it's falling at a constant velocity, what are the forces? Let's see. So you have constant velocity. It means that the Fg, which is down, is equal to the Fd, which is in this case will be up. So they are equal in magnitude, opposite in direction. This is the answer for you. Next question. So here we have an oil drop weighs 1.9 times 10 to the power minus 15 Newton. So this is Fg because it is the weight. You suspend it in an electric field. This is the value of E. What is the net charge on the drop? So you need to find what is Q and how many excess electrons does it carry. How many? We will find the equation to calculate this. Now first we say you have electric field, so the forces are Fg is equal to Fe. So the equation of E is equal to Fe divided by Q. So it was mentioned in the question that Fg is 1.9 times 10 to the power minus 15, and in this case it is equal to Fg, so we can use the same number. Here we have 6 times 10 to the power 3 is equal to, the force is 1.9 times 10 to the power minus 15, and the charge is unknown, so we do shift solve, and Q will be 3.2 times 10 to the power minus 19 Coulomb. Now to the second part, how do I find how many excess electrons? We will say that 1 electron is equal to the charge of 1.6 times 10 to the power minus 16 Coulomb. So what I have is 3.2 times 10 to the power minus 19 Coulomb. How many electrons do I have? I will cross multiply. So here we will say number of electrons will be 1 times 3.2 times 10 to the power minus 19 divided by 1.6 times 10 to the power minus 19. So the answer will be exactly 2 electrons, because you cannot have 1/2 or 3/4 or 0.7 electron in nature. Here is another question. An oil drop carries 1 excess electron and is weighing this much, so this is Fg. What electric field strength do you need to suspend the drop so that it is motionless? So like we said, Fg here will be equal to Fe, and the equation is E equals to Fe divided by the charge, and we have 1 electron, so the charge is 1.6 times 10 to the power minus 19. So here we need to know what is the electric field. We can solve directly. So the force is 6.4 times 10 to the power minus 15 divided by 1.6 times 10 to the power minus 19, and the electric field will be 40,000 Newton per Coulomb. Next we have, you suspend a positively charged oil drop that is weighing this much, so this is Fg, which is the same as Fe, between two parallel plates that are 0.64 centimeters apart. So this is the distance we will need to calculate the electric field. The potential difference between the plates is this much, so this is delta V. What is the net charge on the drop, and again how many electrons the drop is missing? So here we will say again that Fg will be equal to Fe, and we have E is equal to Fe divided by the charge. But here we don't know what is Q, we don't know what is E. So electric field is calculated from the equation. This one will be calculated from E is equal to delta V divided by the distance. So delta V is 240 and the distance is in centimeters. So first we divide by 100, we get 0.0064, and this will be equal to 37500 Newton per Coulomb. So now we have E, this will become E equals to Fe divided by Q. Now this is 37500 equals to Fe is 1.2 times 10 to power minus 14 over the charge. Now shift solve, and Q will be 3.2 times 10 to power minus 19 Coulomb. Now the second part is, again we have one electron has a charge of 1.6 times 10 to power minus 19 Coulomb, and here we have 3.2 times 10 to power minus 19. How many electrons? We will say that the number of electrons will be 1 times 3.2 times 10 to power minus 19 divided by 1.6 times 10 to power minus 19, and the answer will be again 2 electrons. Here we have a question. When the net charge on an oil drop suspended in a Millikan apparatus is changed, so here we have the charge is changed, the drop begins to fall. How should you adjust the potential difference between the conducting plates to bring the drop back into balance? So if the charge is not balanced, it means that maybe Fg is more than Fe in this case. So what do we need to do? We need to increase the value of electric field. How do we increase the value of E? By increasing the value of the potential difference, because we have the equation is E is equal to delta V divided by D. So if this is increased, then this is increased. If electric field is increased, then the force on the charge is increased and you can balance the charge again. So here is the part on the capacitance, and how do you calculate the charge or the potential difference between the plates and the capacitance. This is the equation. So capacitance is in farad, Q is in Coulomb, and delta V is in volt, and 1 volt is equal to 1 C divided by V, and capacitor definition is storing electrical energy device. This is the conversion of the farad unit. Here we have a question. A 27 microfarad, so this is C, capacitor has an electric potential difference, so this is delta V across it. What is the amount of net charge? So you need to calculate what is Q on the positively charged plate of the capacitor. So capacitor actually is like a parallel plate electric field. Okay, so it looks like this. That's the capacitor on the inside. Now we need to calculate how much is the charge. So we start with the equation. C is equal to Q over delta V. C is 27 times 10 to power minus 6, which is equal to Q divided by 45. Now we do shift solve, and Q will be 1.2 times 10 to power minus 3 Coulomb. Moving on, suppose you connect both 3.3, so this is first capacitance and this is the second capacitance across a 24 volt, so this is your delta V, electric potential difference. Which capacitor has the greater net charge on its positively charged plate? So first of all, we start with capacitance 1 will give me charge 1, and it is the same potential difference. So we say capacitance 1 is 3 times 10 to power minus 6 is equal to, how much is Q1? Unknown, and delta V is 24. So we do shift solve, and the charge 1 will be 7.92 times 10 to power minus 5 Coulomb. Now we do the same for the second one. C2 will be giving me charge 2 over delta V. So here we have 6.8 times 10 to power minus 6 equals to charge 2 divided by the same potential. Shift solve again, and charge 2 will be 16.3 times 10 to power minus 5 Coulomb. So both of them are 10 to power minus 5, but this one is larger, so this will be the larger. Okay, now how do I know if C is larger? It means Q is larger if delta V stays the same. Next question. You later find that the magnitude of the net charge on each of the plates for each of the capacitors in the previous problem to be this much. Which capacitor has the larger potential difference across it? So now we have C1 was 3.3 times 10 to power minus 6, and C2 was 6.8 times 10 to power minus 6. The charge for both of them now is the same, so it will be 3.5 times 10 to power minus 4 Coulomb. So in this case, how do I tell if you have higher potential or lower potential? We calculate. So C1 will be Q divided by the first delta V. C1 is 3.3 times 10 to power minus 6, and the charge is 3.5 times 10 to power minus 4. This will give me the first delta V. Shift solve, and delta V1 will be 106 volts. Now let's try the second one. C2 will be Q over delta V2, and this will be 6.8 times 10 to power minus 6, 3.5 times 10 to power minus 4 divided by delta V2. Again, shift solve, so delta V2 will be 51 volt. So from this we can say that if they have the same charge, different capacitance, the higher the capacitance, the lower is the value of delta V. Okay, but Q has to be the same. Next question. Suppose that you apply an electric potential difference, so here you have delta V, across this much capacitance. What does the magnitude of the net charge on one plate needs to be to increase the electric potential difference to this much? So we start with the equation C is equal to Q over delta V. Now C is 2.2 times 10 to power minus 6, and now we need the potential to be 15, but how much is the value of Q? So we do shift solve, and Q will be 3.3 times 10 to power minus 5 Coulomb. So this question we already solved in part 1. Here we have a challenge question. You increase the potential difference across a capacitor from, so this was V1 to this was V2. As a result, the magnitude of the net charge on each plate also increased by this much. So this is the value of the increment. So this is delta Q. I don't know how much it was, I don't know how much it is now, but I know that it has increased by this much amount. What is the capacitance of the capacitor? So we say C is equal to the change in Q over the change in delta V. Now how much is the change in delta Q? It is 2.5 times 10 to power minus 5. And how much is the change in the potential? It will be 14.5 minus 12.0. Delta V is actually V2 minus V1. Now we calculate. The answer will be 1 times 10 to power minus 5 farad. Next question. What is the magnitude of the net charge on each conductor plate that have this much C capacitance when a potential difference this much, this is delta V, is applied across So C is equal to Q over delta V. Do we have C? It is 0.47 times 10 to power minus 6 equals to, charge is unknown, delta V is 12, so we do shift solve, and Q will be 5.64 times 10 to power minus 6 Coulomb. This is the end of the MCQ questions. We will go to the free response questions. Wave properties. We start with this topic. So we have more than one property of the wave that we need to know and understand. So let's start by drawing a wave. Here you have one wave, one full wave. We can say that the distance from the start of the top and the bottom is one wavelength. Now from here to here, this is the amplitude. This point, or this point, these are the equilibrium points or the 0 points. And how many waves do we have is called the frequency. The maximum point is called the crest. The minimum point is called the trough. Trough with F. We say F here. Okay? Now the wavelength is the distance from trough to trough or crest to crest. So basically it is the shortest distance between two points that are repeating themselves on the wave. So this is a wavelength. And then how do we calculate the speed? Speed can be calculated by two equations, either distance over time, or we can say lambda times the frequency. This one is valid in cases and the other one is also valid in some other cases. And then we have something called a phase. So a phase is how much difference do you have between two waves, for example. So a phase is basically telling you that if you have waves that are moving together, or one of them is ahead of the other, or one of them is late than the other. Now period. Period is the time for one wave only, the time it takes for the motion to complete one cycle. So here we say it is time for one wave or one cycle. And how is it related to the frequency? Frequency is the number of waves. So frequency is how many waves do you have, or we say the number of waves that we have. So it is equal to the inverse of the period. Period is calculated in seconds, frequency is calculated in hertz, and here we have hertz is equal to 1 over second or second inverse. So the hertz is equivalent to 1 over second or s minus 1. And then the wavelength, we find the wavelength from the speed equation. Wavelength is in meter, frequency is in hertz, and the unit for the speed is meter per second. Now, how do I know when is the number equals to a wavelength and when is the number equals to a period? Here I need to check what do I have on the x-axis. So first thing, you check what is the x-axis. If it's meter, then this is lambda. If it's time, then this is period. So wavelength will be from two points that are the same. You can say from here to here or from here to here. This is also wavelength. So here wavelength is equal to how much? Start, repeat, that's it. So my wavelength is 0.4 meter. Now for the period we do the same. So we can say from here all the way to here, or you can start from here all the way until you start repeating the same shape. So this number is 0.4, so a coincidence, but this one is 0.4 seconds and not meters. A sound wave produced by a clock chime is heard 515 meters away 1.5 seconds later. So this is a normal distance, this is a normal time. Based on these measurements, what is the speed? So in part A, V will be distance over time. So the distance here is 515 over 1.5, and the answer will be 343 meter per second. Now we go to part B. The sound wave has a frequency, so this is f. What is the period? Period is the inverse of frequency, so we say 1/436, and the answer will be 2.2 times 10 to power minus 3 seconds. Part C. What is the wavelength? Wavelength is equal to V over F. So we calculated V is 343 and F is 436, and the answer will be 0.78 meters. نروح لهذا السؤال. How are the wavelength lambda, frequency F, and the speed V of a wave related? أول شيء they are related by the equation lambda times F is equal to the velocity. How do they depend on the medium through which the wave is passing and the type of the wave? فعندي هنا ال V change إذا تغير الميديم، وال wavelength أيضا change if you change the medium. F stays the same. Take an example. You are in one class right now, so you are 30 students, and then you go to the lab. If you go to the lab quickly or you go slowly, your velocity will change because you are faster or you are slower, and the distances that you are covering based on your speed will be different. But you started with 30 students. When you go to the lab, you will still be 30 students. So frequency is the number of wave and it does not change. Here we have a question. What is the speed of a periodic wave disturbance that has a frequency? This is F, and the wavelength, this is lambda. So here we say F times lambda 3.50 times 0.7, and the answer will be 2.45 meter per second. Here we have, how does increasing the wavelength by 50% affect the frequency of the wave on a rope? So we start with lambda equals to some number, let's say 1 lambda, and this is lambda 1, and then lambda 2 is now 50%. So if it is 1, 50% of 1 is 1/2, صح? We will have 1, the original, plus the 50%, which is 1/2. So my lambda is 1.5 lambda in this case. Okay, and then we can start with the velocity of V is equal to lambda F. This is before we do any change with lambda 1, and then we will see what is the frequency, and then after, when we have lambda 2 and the frequency. So here we will have 1.5 of lambda, and I need to know how is the frequency going to change. Now we divide by both sides. V will go with V, lambda will go with lambda. Now here we have 1 on the left side, and we have F1 divided by 1.5 of F2. Now take F2 to the other side, you will get 1.5 F2 is equal to F1. I want the value of F2 only, so this becomes F2 is equal to, طبعا 1.5 is equal to 3/2. So here we can say it will be 2/3 of the value of F1. This is the answer for the first question. Here we have the speed of a transverse wave in a string is this much, so this is velocity. If a source produces a disturbance that has a frequency, this is F, what is the wavelength? So we say V is equal to lambda F, and V is 15 meter per second equals to lambda times F, which is 6. Shift solve, and lambda will be 2.5 meter. So here we have 5 wavelengths are generated every 0.1 seconds. So let's say that from here to here, this is 0.100 seconds, and you are starting from here and you have one wave, 2 waves, 3 waves, 4 waves, and 5 waves. Now, how much is the time for one wave? Time here, we will say the period will be to divide 0.100 over 5, so we get 0.02 seconds. So here, this wave will be 0.02 seconds to complete from this point to this point, and then the next one will be 0.02, 0.02, 0.02 until we finish the distance. What is the speed of the wave if the wavelength of the surface wave is this much? طبعا this is centimeter, so first we say 1.2 divided by 100 and we get 0.012 meter. This is my lambda. Now we need to find V. V will be equal to lambda times F, but I don't have frequency, I have T, so first I will say F is equal to 1 over T, which is 1 over 0.02. This will be 50 Hertz. Now V is unknown, lambda is 0.012 and the frequency is 50, so the speed will be 0.6 meter per second. Next question, a periodic longitudinal wave that has a frequency of, so this is F, travels along a coiled spring toy if the distance between successive compressions, successive means one after the other, so here this will be lambda. What is the speed? So V is equal to lambda times F, and here we have direct substitution, 0.6 times 20 and we get 12 meter per second. Here we have, how does the frequency of a wave change when the period of the wave is doubled? So we start with before and after. So here we have F1 is equal to 1 over 2. Now F2 will be when you get the period to be double, so it will be 2 times the period. Now we divide left side by right side. Here T will go with T. Now we have F1 over F2 is equal to 1 over 1/2. Do cross multiplication. You will have F2 is equal to 1/2 F1. Next question. Describe the change in the wavelength of a wave when the period is reduced by 1/2. So now you have T becomes T over 2. So here we start with V is equal to lambda F, and we know that F is equal to 1 over T. Now we can rewrite the equation to be lambda divided by T. Now we take this to be the before and this to be the after. Divide them. So here we will get V equals to lambda over T, and here we say V is equal to lambda over T over 2. Now V will go with V, and we need to know how does the wavelength change. So here we have lambda 1 and here we have lambda 2, and now T will go with T. So what do you get is 1 on the left side equals to lambda 1 over lambda over 1/2. So we do cross multiplication. We get lambda 2 divided by 1/2 is equal to lambda 1. Now take the 1/2 to the other side, so you get lambda 2 is equal to half of lambda 1. Next question. If the speed of a wave increases to 1.4 times its original speed while the frequency remains the same, how does the wavelength change in this case? So here we have V is equal to lambda F. If the velocity increase, wavelength increase, and this stays the same. Okay, if velocity decrease, this will decrease and this will also stay the same. Now if you increase velocity by 1.5, this will increase again by 1.5. So we say that it will increase by the same amount, which is 1.5 times. This question we already solved in part 1. Now we go to resonance. So when do you get resonance is when you have forces applied to a vibrating or oscillating object at the same intervals that are equal to the period of oscillations. So this will help increase the amplitude and the loudness of the sound. So resonance gives you actually a very higher sound. Like we defined before, we said pitch is the highness or lowness of a sound. This part we have already explained in part 1. This one explained in part 1. In part 1. In part 1. In part 1. Same in part 1. And this is also in part 1. In part 1. In part 1. Same for the resonance on the string is in part 1. Let's start here with Doppler effect. Doppler effect is some effect that you hear or see because there is an object that is moving with the sound on it. So here you say that there is a movement that changes the sound that you are hearing. Either the sound is higher or lower, or you hear a high pitch sound or a lower pitch sound. Now let's say that you have an ambulance that is emitting a siren sound and it's coming to you. So in this case, what do you hear? You hear a high pitch sound. So this means that you hear a high frequency. But if you are on the other side, you will hear a low pitch, a low frequency. So Doppler effect talks about objects moving with a sound, either towards you or away from you. Now here is the equation. This is what you hear. This is the frequency of the source. These two are the same. They are speed of sound in whichever medium. This is your velocity. This is source velocity. So here we have Doppler effect talks about sound or light. So we have two scenarios. Either you come closer or you are going away. Same goes for the light. So let's say you are standing and there is a car that is coming closer to you. You will hear a high frequency. If it goes away, you will hear a low frequency. If it is light and the source is coming to you, you will again see high frequency. You don't hear it because it's light, you see it. So a high frequency, we say that you are experiencing a blue shift, as in the object appears more blue to you. Now if the object is going away, again you will see low frequency. Then you are observing red shift, as in the object appears to be more red than its original color. Now we go to the coordinate system. So here, take it as a rule, the positive direction is from the source to the detector. Let's say this is the car, this is the source, and this is the detector, this is you. Now where is positive? From the source to the detector, this is positive direction. If you are moving away, then this is negative direction. Why do I need this? For the velocities. Now if you are going closer to the source, then your velocity is negative. Let's say that the source is going closer to you, it's moving in the positive direction, so Vs will be positive. Let's say the source is going away from you, it's in the negative direction, and let's say you are going away from the source, so your velocity is positive. Here is an example. A guitar plays sound C above middle, so this is the source from the guitar. So this is F, S, while traveling in a convertible at 24.6 meter per second. Now we need to define the direction. If the car is coming towards you, so here is the car, this is the source, and you are the detector, and we said that from here to here, this is positive direction, and if you go away, this is negative direction. Now it's coming towards you, so this direction is positive for Vs. What frequency would you hear? Now the equation is Fd is equal to Fs V over V minus Vd over minus Vs. Now we substitute how much is the source frequency, 523, and the speed is when the temperature is 20. So here we take it from the table, 343 divided by 343. This is in air at 20 Celsius. Now, are you moving? No, you are not moving. So this is 0. And the source is in the positive direction. So we leave the number as it is, 24.6. Now, calculate. The answer will be 563 Hertz. Let's evaluate. The source is coming to me, so I have to hear a high pitch sound, which in my case the number is higher, so that is a correct answer. Now here it says repeat example 1 problem but with the car moving away from you. Now if it's moving away from you, it means that your velocity Vs is in the negative direction. Now what do you hear? Same thing, but now we will have a positive in the denominator. So we substitute 523. We have 343 minus 0 over 343 minus from the equation, but this will be negative 24.6, and the answer will be 488 Hertz, and the number is going down, so you are hearing a lower pitch because the car is going away from you. Let's see this question. You are in an automobile, like in the one in figure 7, traveling towards a pole-mounted warning siren. So this is the source. If the siren's frequency is this much, what frequency do you detector hear? Now use this as the velocity. So we say Fd is equal to Fs multiplied by V over V minus Vd over Vs. So here the source is 365. Now the speed is 343 over 343 minus, are you moving? Yes, you are moving to the source. So this is source, this is detector, and this is the positive direction, but you are moving in the negative direction, so your velocity is negative. So here we will say negative velocity of 25. And is the pole moving? No. So Vs is equal to 0 minus 0. So the answer will be 391 Hertz. So you are hearing a higher pitch sound. Next question. You are in an automobile traveling at 55 miles per hour. طبعا we don't take this, we take meter per second. So this is my Vd. A second automobile is moving towards you at the same speed. So this is also Vs. Its horn is sounding at 475 Hertz. What frequency do you hear? And use this to be the velocity of the sound. So we draw, this is the detector and this is the source, and we said from the source to the detector this is positive and the other way will be negative. Now we said that you are moving, let's say, in this direction, and a source is moving towards you in the opposite direction, so this will be positive Vs. And when we substitute, Fd is equal to Fs V over V minus Vd over Vs. Fs is the source, which is 475. Fd is 343 divided by 343. Now we have negative 24.6 divided by 24.6 for the source speed, and the answer will be 548 Hertz. Next question. A submarine is moving towards another submarine at this velocity. So we have some velocity, we will see for who. It emits 3.50 megahertz. This is mega, which is times 10 to power 6 positive. So this will be Vs. What frequency would the second sub, which is at rest, so this is Vd, detect? And the speed of the sound in the water is this number, so this is V. Now we say source to detector, this is the positive direction, and the other way is the negative. Now Vd is 0, but the source is coming towards another submarine, so this velocity Vs will be positive. Now we substitute directly. We have 3.5 times 10 to power 6 multiplied by 1482 over 1482. Now we are not moving, we are the detector, and the other submarine is moving at 9.2, so the answer will be 3.52 times 10 to power 6 hertz, or we can write M in this case, megahertz, and 3.2 megahertz. Last question. A trumpet plays middle C, so this is the Fs. How fast would it have to be moving to raise the pitch? Raise the pitch as in, this is the frequency that you are hearing, and it should come towards you, and this is the speed. So we say that source to detector, this is positive and away is negative. Let's assume that you are not moving and the source should come to you because you are hearing a higher sound, so Vs should be positive. You are hearing 277 and the source is 262, and the speed is 343 over 343. You are not moving, but you need to know what is the velocity of the source. So we do shift solve, and Vs will be 18.5 meter per second. So this question is solved in the previous video. Let's see question 7. The eardrum moves back and forth in response to the pressure variations of a sound wave. Sketch a graph of the displacement of the eardrum versus time for 2 cycles of 1 kilohertz tone and 2 kilohertz tone. So the graph we will draw will look something like this. So we will have displacement here in meters, and we will have time here in seconds. Now the first one needs to be found in terms of period. So we find period 1, which is equal 1 over f, 1 over 10 to the power 3 because kilo, and this will be 1 times 10 to power minus 3 seconds. Now we find the second period, which is equal to 1 over 2 times 10 to power 3 2 kilohertz, and this will be 0.5 times 10 to power minus 3 seconds. Now we can draw for a period of 1 millisecond and another period for half millisecond. So let's say this is my 1 times 10 to power minus 3 seconds. We can say the first wave can start like this and then end here. So this is one full wave. This will be for T1. Now for the second wave we need 0.5 times 10 to power minus 3. So it will be, we can start from the same point and then it will be something like this. So it ends here, and this is for period 2. Now we go to question 8. Effect of a medium. List 2 characteristics of sound that are affected by the medium through which the sound passes, and 2 characteristics that are not affected. So if it's affected, this is speed and wavelength like we mentioned before. Not affected, which is the period and the frequency. Let's see question 9. Decibel. How many times greater is the sound pressure level of a typical rock concert, which is at 110 dB, than a normal conversation, which is at 50 dB? So how do we know? We say that every 20 dB is 10 times. So when you go from 50 to 60 and 70, this is times 10. Now from 70 to 90, this is another 10. Now from 90 to 110, this is again the sound increase by 10 for every 20 dB. So here we say that the increase will be 10 times 10 times 10, which will be 1000 times larger. These are the answers. Moving on. In the 19th century, people put their ears to a railroad track to get an early warning of an approaching train. Why did this work? We said that the sound goes fast in solid, so when they put their ears on the ground, this is solid, and the sound gets there faster. A bat emits short pulses of high frequency sound and detects the echoes. So sound will go in one direction and then comes back. In what way would the echoes from large and small insects compare if they were the same distance from the bat? So large insects will reflect high sound energy and small insects will reflect small energy or low energy. In what way would the echo from an insect flying towards the bat differ from an insect that is flying away? So if it's flying towards the bat, it means it will reflect high frequency. Flying away, it will reflect low frequency. Question 12. Can a trooper using a radar detector at the side of the road determine the speed of a car at the instant the car passes by? Explain. So if we are calculating at an instant, no, we cannot determine. Why? Because for Doppler effect, you need to know if the object is approaching or going away. So these are the answers. This question is already solved in video 1. Now we go to the electric field. We said that electric field is a property of the space that is around the charged object that is either positive or negative. So if I have a positive charge, how does the electric field look like? It will start from the charge and go away. If I have a negative charge, it will start from infinity and come or close up to the charge. Now if you are closer, your electric field is higher. If you are away, your electric field is lower. Now there are two equations for electric field. The first one is this one. The second one is E is equal to K capital Q over R squared. Now this one is mostly for Q, which is the source, the one that is creating the electric field. This one here, small q, is for a test charge. Now how can we represent them? Let's say you have a positive charge. This is creating the field in all directions. So this will be the source for the electric field. Now if I bring a small charge here, it will be repelled, so it will go away from the source. This is the test charge, and the force is the same force that is being affected because of the electric field. So here this is electric field that is made by Q, and wherever you are, you can tell if the electric field is at a higher value or a smaller value. Here this is the same generated electric field, but when you put a test charge, you calculate how much is the force affecting this test charge. So we go for the unit. Electric field is measured in Newton per Coulomb. This is K, which is 9 times 10 to power 9. This is Q in Coulomb, and this is distance in meter. Here is the same, Newton per Coulomb. This is Coulomb, and this is Newton. Like the force, electric field is also a vector quantity, so you draw the line in a specific direction. Let's take a situation where you have a source which is positive. So the field will look like this everywhere. Now if you put a small positive test charge here, where does it go? Does it come closer to the charge or away? It's positive, so it will go away. So we always say that positive move with the line of the electric field. So at this point, the electric field looks like this. So it will move with the line. So if we have a negative charge here, this is also a test charge. Where does it go? It will be attracted to the positive. So a negative charge always move against the line of the electric field. So this is electric field going away, but the charge is being attracted. Now let's try with a negative charge. How does that work? It will be the same. So electric field will go to the charge in this case. Okay. Now if you put a small test charge, it will be attracted. So this is the direction of the force. It is in the same direction of the electric field. Now let's put a negative charge, negative and negative. It will go away. So this is the force and this is the electric field. It will always move in the direction opposite to the electric field. This part we already explained before. Let's solve these questions. We have a positive test charge. So this is small q is in an electric field that exerts a force. This is F on it. What is the magnitude of the electric field at the location of the test charge? So here we say E is equal to F over Q. F is 2 times 10 to power minus 4. Q is 5 times 10 to power minus 6. And the answer will be 40 Newton per Coulomb. Next question. A negative charge, now this is negative Q, of this much, this is the value, experience a force which is this much, this is force, to the right. So here is my negative charge and the force is in the right direction. In an electric field, what are the field's magnitude and direction? So because we have a force and a test charge, we use this equation, F over Q. Do I have the force? Yes. Do I have Q? 2 times 10 to power minus 8. So electric field will be 3 times 10 to power 6 Newton per Coulomb. Now to find the direction. This is negative charge. It will move in the opposite direction to the electric field. So electric field will be against the force. So we say it is in the left direction. Here we have a positive charge of this much. This is Q, is located in a field. This is E, directed towards the south. So south is down, this is south, and this is the electric field direction. What is the force acting on the charge? So we say E is equal to F over Q, and we have E, which is 27, F is unknown, Q is 3 times 10 to power minus 7. We shift solve, and the force will be 8.1 times 10 to power minus 6 Newton. In which direction? This is positive, so the force will be in the same direction. So this is the force, this is the direction of the force, so it will be also south. Now this table is very easy. I will leave it for you to answer. Here you have a test charge. The value of Q is here, the value of the force is here, and the value of the electric field is here. So you have two of them. Calculate the third one. Here we have a negative test charge which is placed in an electric field as shown in the figure. It experienced the force as shown. Here is the force. What is the magnitude of the electric field at the location of the charge? So here we say E is equal to F over Q. Now we need to find E. How much is the force? 0.080 Newton divided by, we do not put the negative sign, so only 5 times 10 to power minus 6, and the electric field will be 1.6 times 10 to power 4 Newton per Coulomb. Now let's see where is the direction. Here is my positive charge and the electric field looks like this. Now where is the force going to be on the charge? It will be in this direction. Challenge: you are probing the electric field of a charge of unknown magnitude and sign. You first put a test charge which is 1 micro, and then you put a double charge which is 2 micro. would you measure the same force on the same place with the two test charges? Explain. First of all, here is my positive, let's say, source that is creating, this one creates the electric field. Okay, so electric field value does not depend on the test charge. Now you have a small test charge here. If you get a larger test charge, the force will be different. Yes, because you have different charges, and when you calculate F is equal to K Q1 Q2 over R1 and 2 squared, if you change the Q to a larger one, then your force will be changed. So here, no, you will not find the same force because force depends on the value of the charge. So if you change the charge, you change the force on it. But now we are talking about the field. Did we change the source? No. So in this case, we will measure the same field. Yes, you will measure the same because the source has not been changed. What you change is the test charge and not the source. So here we can say that if you change source Q, then E will change. But if you change test charge Q, then F will change. Next question. What is the magnitude of the electric field at a position that is this much, this is R, from this much charge? So this is Q, and to find E, we will say K Q over R squared. Now K is 9 times 10 to power 9 times Q is 4.2 times 10 to power minus 6, and the distance between them is 1.2 squared. The answer will be 2.6 times 10 to power 4 Newton per Coulomb. Next question, we have what is the magnitude of the electric field at a distance which is twice as far from the previous problem? So now my R is equal to 2 times 1.2, which is equal to 2.4 meter. Now we do the same thing. E will be equal to K Q over R squared. K is 9 times 10 to power 9 times 4.2 times 10 to power minus 6 over 2.4 squared, and the answer will be 6.5 times 10 to power 3 Newton per Coulomb. If R increase, electric field will decrease because you are going away. Next question, what is the electric field E at a point 1.6 meter east to a charge of this much? So here is my charge, which is positive, and now we want east, which is, let's say here is the point, x is equal to 1.6. It will be to the right because it's positive charge. The line will go from the charge to the point. Now to calculate K Q over R squared, you have K is 9 times 10 to power 9, Q is 7.2 times 10 to power minus 6, and the distance R is 1.6 squared. The answer will be 2.5 times 10 to power 4 Newton per Coulomb, and like we said, the direction will be east. Here we have the electric field that is 0.25 meter, so this is R, from a small sphere is this much, this is E, towards the sphere. Towards the sphere, here is my sphere, and at the point which is x is equal to 0.25 meter, the electric field is towards the sphere, so this is a negative charge. What is the net charge on the sphere? So we say E is equal to K Q over R squared. E is 450, K is 9 times 10 to power 9, Q is unknown, divided by distance, which is 0.25 squared. Now shift solve, and Q will be 3.1 times 10 to power minus 9 Coulomb, and like we said, it's a negative charge. Next question, how far we are asking for R from a point charge which is this much, this is my Q, must you place a test charge in order to measure a field of this much? So here we say E is equal to K Q over R squared. E is 360. K is 9 times 10 to power 9 times 2.4 times 10 to power minus 6 divided by the distance, which is unknown. We say R squared. Shift solve, and R will be 7.7 meters. Explain why the strength of the electric field exerted on a charge Q by the charged body Q is independent of the charge on Q dash. Use the mathematics to prove your point. So here we are talking about the source Q and the small test charge Q dash, and why does it not affect the other one? Because when you calculate E here, we are calculating from the source charge, which is this one basically, Q, or we can say Q capital. But when we calculate the force that is affecting the small q, in this case, we are checking for what is the force that is affecting the small charge in this case. What is the magnitude of the electric field E exerted on a test charge as shown in the figure? So this is my test charge. So this is my source, this is my test charge, and this is the distance R. So we need to find how much is E. E will be K Q over R squared. Now K is 9 times 10 to power 9 times the charge is only the magnitude, so 3 times 10 to power minus 6 divided by the distance, which is 6 squared. The answer will be 7.5 times 10 to power 2 Newton per Coulomb. Challenge: you place a small sphere with a net charge of this much, so this is my Q, at one corner of a square that measures 5 meters on each side. Okay, so we have a square here, and we put a charge here, and the sides are 5, 5, 5, and 5. What is the magnitude of the electric field at the opposite corner of the square? So we want to find how much is the field at this point. So how much is this? This is calculated by 5 square plus 5 square, the distance. Now E is equal to K Q over R squared. K is 9 times 10 to power 9. Q is 5 times 10 to power minus 6. Distance is square root of 5 squared plus 5 squared, squared again, and the answer will be 6.4 times 10 to power 3 Newton per Coulomb. So this is, we already discussed before. Electrostatics is the study of electric charges that can be collected and held in one place. I'll leave the rest for you to read. Here we have the types of objects. We have neutral, positive charge, and negative charge. If an object has a positive charge, it means the proton is larger in numbers than the electron. If you have a negative charge object, it means that the protons are less in charge than the electrons. And when you have a neutral object, then the number of protons is equal to the number of electrons. Here we already explained this before. This part talks about the forces on charged objects. So you have like charges repel, unlike charges attract, and charges affect each other. They apply forces on each other, same magnitudes, opposite directions, and so on. Here we have the device, which is the electroscope. It tells you if you bring an object closer to the electroscope, is it charged or not. So we have 3 ways to charge. Charging by conduction, where you are touching the knob of the electroscope, and then you have charging by induction, where you bring it closer to, but you are not touching it. I will send you a video for this lesson, explain all the details for all the situations. Now let's see, we have 2 spheres that are neutral. Neutral means that positive is equal to the negative amount of charge. Now if we make them connected together and then bring a negative rod, the negative will separate positive from negative. These are conducting spheres, so the charge is easily moved. So here you will have all the positive closer to the negative and all the negative away from the negative. Now keep this rod closer by and then separate both spheres Now you have one which is fully negative and one which is fully positive. Here we have grounding. How do you ground the electroscope? Basically, you just need to touch with your finger, or you connect it to the ground. We already answered these questions in part 1. I'll leave the answer for you. Here we have an apple contains approximately 10 to the power 26 charged particles. Why do two apples not repel each other when they are brought together? So they have this much charged particles, but they also have the same number of positive charge and negative charge, so they cancel each other and they become neutral. Suppose you hang a long metal rod from silk threads so that the rod is electrically isolated. So here you have, this is your rod, it is tied to a thread and it is hanging. You then touch a charged glass rod to one end of the metal rod. Describe the charges on the metal rod. So this one here is metal, and you will bring another rod which is glass. So when they are in contact with each other, the glass will take the negative charge from the metal and the metal becomes more positive. Charging by friction. You can charge a rubber rod negatively by rubbing it with wool. What happens when you rub a copper rod with wool? So we said that there are materials that have tendency to be positive or tendency to be negative. And as long as it is in contact with my hand, if I am holding it with my hand, then I am constantly discharging the copper rod. Here are the answers. In an electroscope being charged by induction, what happens when the charging rod is moved away before the ground is removed from the knob? So when you take the rod away first, you are allowing the ground to take all the remaining charge. The rod stays because it keeps some of the charge hanging at the top of the electroscope. Now there is nothing holding this charge at the top. It will go to the ground. Question 19. Why do the leaves of a charged electroscope rise to a certain angle and no further? Because as the leaves go higher and higher because of electrostatic force, there is also Fg that is acting down and keeping them at a certain level. Question 20. Attraction of neutral objects. What properties explain how both positively charged objects and negatively charged objects can attract neutral objects? So this question says that even though you have a neutral object, it can still be attracted or repulsed. How does that happen? So a neutral object basically has a charge still. Even though it's neutral, it still has a charge. So if I were to bring a negative rod, what happens here? This negative rod basically will bring the positive closer to it and repel the negative away from it. Question 21. Charging an electroscope. How can you charge an electroscope positively using a positively charged rod and then using a negatively charged rod? So in the first case, you touch it, you give it your charge. This is part 1. Now, how do you charge it positively but using a negative rod? In the second case, you will do induction and at the same time you will have the ground connected. These are the answers for you. This is the end of the second part and the whole EOT file. Wish you all the best and hopefully you get full marks.